Okay, up until now, the only way that we could figure out the chances of something happen is to run a simulation and do it over and over and many, many, many times. Yeah, flipping a coin, the probability of getting heads. The only way we really know what the probability of getting heads is to flip a coin 1,000 or 2,000 or 3,000 or 5,000 times. And we know if we do it a lot of times, whatever that probability comes up to, that's the probability of getting heads. The birthday problem, the chances of a birthday match. Run that repetition thousands and thousands and thousands of times. That's the way you can find out the probability of getting a birthday match given a certain number of people. Got to be an easier way. And that's what we're going into now. We're going to go into certain mathematical models. That's a shortcut to figure out, I don't want to have to run a simulation 1,000 times. Is there a way to figure out how that thing would end up before I even do it? All right, the first one and the most, the easiest and the most important one is just this basic rule of probability. And it says P sub A. So first of all, we're going to be doing a lot of symbols in here. So let's make sure you understand what these symbols mean. When you see a P and then these parentheses and A, what it means is, hey, what's the probability of event A happening? Like if I flip a coin and I want to know the probability of heads, I might write the probability of heads. Or I might take a shortcut and just say the probability of getting a heads. Okay? So when you see that symbol, it means, hey, what is the probability of that event happening? The next one now, in our book, you'll see this little C on the top of an event on the test, and more often you'll see this little hyphen above it. And what this means is we want to know what the probability of event A not happening. Okay, it's called the complement. So if you see something like that, they want to know the probability of it not happening. We'll talk more about that in a minute. Upside down horseshoe, upside down U, okay, that's your AND symbol. So I want to know the probability of an event A and B happening. Like we just talked about, Jason, that would be the probability of getting a heart and a queen. Okay, it means they both have to happen. We'll talk more about that real soon. And the U symbol, that stands for union, and it's the probability that either event A or event B happens. Okay, we'll be talking about that a little bit actually today. Okay. All right, so the most general and basic rule for probability is this one. If I want to know the probability of an event happening, and I don't want to run a simulation for the rest of my life to figure it out, here is the formula that will give it to me. You find out how many times a certain event will happen and divide it by the total number that's in the sample space. We worked with sample spaces yesterday and figured out how many were in the sample space. Let's take the most simple example. Let's say I flip a coin and I want to find out the probability that it's going to come up heads. All right, for my denominator, how many different things could possibly happen if I flip a coin? There's just two of them, right? And then how many of those things is the event I'm looking for? A heads. How many of those are there? One. So there's a 1/2 chance in the long run that I flip a coin and I'm going to get heads. Let's step it up and change it a little bit. Now this was the one you worked on last night. Okay, and it was rolling 2 dice and adding them up. Okay. So what is the chance that if you roll 2 dice and add them up that it's going to come up snake eyes? 2. If you add them up. Well, from your chart last night, first of all, how many total ways can it possibly happen? If you roll 2 dice, how many elements of the sample space are there? You roll 2 dice. How many elements of the sample space are there? 2? Oh. If you roll 2 dice, how many ways can it happen? Go back to multiplication rule, right? I'm rolling 2 dice. How many chances do I have for the first one? 6. How many for the second one? 6. Multiply them together. Weren't there 36 total things that could happen? 36 elements of the sample space. Now, of those 36, how many occurrences were there of getting exactly 2 as the sum? 1. There's your 1. Okay? So the probability that you will roll 2 dice and they'll add up to 2 is 1 over 36. I don't know what that is, a little over 2%. So we could run the simulation. You could roll 2 dice 1,000,000 times. What's going to happen is that percent of the time is going to add up to 2. How about 3? How many occurrences on your chart are there of event getting 3 as your sum? There were 2 of them over your 36. Obviously that could be reduced Okay, but we'll just keep it like that for now. All right, go ahead and complete your probability chart. Remember, you had that little pattern, right? There were more and more ways it could happen up till 7, and then it went back down the other way. So this is in the long run. Many, many repetitions. Michael, if I roll 2 dice 36 times, am I going to get a 2 exactly one time? Matthew, I'm sorry, Matthew. If I roll a dice 36 times, if I roll a die 36 times, what's the probability that I'm going to get exactly 1? If I roll a dice 36 times.
In the long run.
Yeah! I'm only going to roll it 36 times. Let me say it another way. If I roll it 35 times and I never get a sum of 2, does that mean the next time I roll it, I'm guaranteed of getting a sum of 2?
No.
No. Okay? Does everybody understand what Joe just said? This is in the long run. Many, many, many times it'll come out to whatever that percent is. Okay? All right, let's do another one. You guys do this. Based on the activity that you just did, you have all those numbers on your paper right now, all the different ways it can happen. Here's what my question will be. I want to know the probability of getting a certain number of 3s. Okay, so number of 3s. So when I look at my string of 3 numbers, how many 3s could I possibly get? We're going to build our sample space here. How many 3s could I possibly get? Fred. It's you again.
How many 3s
could I possibly get?
out of that?
No, in the warm-up. The one we did for the warm-up. How many 3s? We're going to build the sample space now, this side. So how many 3s are possible? I could get, if I look at my 3 numbers, I could have
3.
I could have 3 3s. They all could be 3s,
yeah,
right?
But you get 1. Wait, what?
I'm so confused. Come on, Jimmy. Come on.
That?
I messed you up.
This is just confusing.
The question that I'm asking is, when you look at the 3 numbers you have there,
yeah,
okay, how many of the number 3 could I have?
We could get 1
Good.
per spin.
Correct, but I'm looking at my 3 numbers. Let's do a different number. Let's do 2s. How many 2s I could have?
You could get.
So I'm looking at my 3 numbers.
3 2s.
You could have 3 2s.
Total.
Could. Any other possibility?
You could have 2 2s.
You could have 2 2s. You could have 1 2.
Or you could have 0 2.
You could have 0 2. We built the sample space there. Okay, Jackson built the sample space for us.
The warm-up said you had to have 1 of each number.
No, did it? Did the warm-up say you had to have 1 of each number?
1, 2, 3.
Yeah, you had to have a 1, 2, or 3, but not necessarily. Your 27 could have all. All right, so what I want you to do, we're going to change this to 2. What's the probability for the number of 2s that you have? I want you to build the probabilities here. So what would based on our probability rule, you have to go through your list. What's the probability if you play that spinner game, you're not going to get any 2s? What's the probability if you play that spinner game, you're going to get exactly 1 2? What's the probability you play that spinner game, you'll get 2 2s? And then what's the probability if you play that spinner game, you're going to get all 2s? Using this general probability. What's our denominator going to be? It's going to be 27, right? Wasn't there 27 possibilities in the sample space? Herman, how many of them had 0?
8.
That's good. How many of them had 1? Anybody got 1 yet? 11, not sure. 11 over 27. How many were 2s? 7? How many of those strings? Huh?
At least, or
No, not at least. A total of two. Total of 2 2s. 6? And how many of those 27, all 3 of them were 2s? Huh? There's just one of those. I can tell you right now that this is not correct. We got a couple of these wrong. Yes.
Well, mine adds up to 27, or mine adds up to 1.
Okay, but these don't. What is yours?
Well, I have 8, 11, 7, 1.
We have 7 here.
Yeah.
12.
That one works.
12.
I think this one is 12. Though.
8,
It should be
12,
12,
6.
6, 1.
And I think that's
What
it.
the heck?
Just be careful. You just got to count carefully. Okay, so that's the idea. If you know what the total number of things are in your sample space, and you can calculate how many for that particular event, if you want to figure out the probability of that event happening, okay, it's just that fraction. Okay? All right, now we're going to introduce several rules of probability for you. Okay, and there's a whole bunch more coming. Okay, like I said, I'm going to keep these up here, but let's explain what these things mean. First of all, rule number 1. When you come up with a probability for something, it has to be somewhere from 0 to 1. 0 meaning it's impossible, 1 meaning it's for sure going to happen. In other words, those clowns that tell you they give 110%, that's impossible based on our rules for probability. 110% would be 1.1, wouldn't it? Okay, no good. So don't ever buy it. You also can't have a negative probability. Okay, so probability has got to be at something between 0 and 100%, including 0 and including 100. Okay. Rule number 2. What's the probability of getting the sample space? Okay, what's the probability of the sample space? Well, that's this. If I have every possible thing that can happen, I'm rolling 2 dice, aren't these all the possibilities that could happen? If I add up all of their probabilities, it's always going to be 1. You saw that yours added up to 27 over 27. That's a good thing to check. Okay, you had one of them off on both of them, but that's one thing that has to be. Okay. One of the questions that you might be asked, I think you are asked tonight. So this is 27 over 27, which is 1, right? If I don't give you that, and you know this is all the elements of the sample space, do you know what that one must be? Sure. Okay, we have subtracted from 1, and that must be the one that's left. Okay, so if you have all of the elements of the sample space here, okay, you're guaranteed that the probability of all of those things happening is 1. Okay, if any of those things happen as well. All right, the next one, this one's not so bad either. It's called the complement rule. I'm asked, the probability that something does not happen is equal to 1 minus the probability that it does happen. If I said the chances that it's going to rain today is 30%, what's the chances it's not going to rain today? 70%. You just take 1 minus that particular probability. Okay, now, just like we've done in the past, anytime you use one of these probability rules, when you're showing your work on your homework or on the test, you first write the formula. So the probability of it not raining today is equal to 1 minus the probability of rain. In this problem, it would be 1 minus 30%, so it's 70%, and then you'd write a sentence talking about the 70%, 75%, 70% chance in the long run that it will not rain today. So that's what I'm going to be looking for on your homework tomorrow. When you use these formulas, make sure you write the formula first and go on. All right, first, really, I think, kind of confusing thing today. This new word is called mutually exclusive. What does it mean? If you have 2 events and they have nothing in common, okay, they both cannot happen. We say those events are mutually exclusive. Another fancy word for this is disjoint. If 2 events cannot happen at the same time, we say they're mutually exclusive. Let me give you an example of events that are not mutually exclusive. What if I said one of the events is you love football, and another event is you love hot dogs? Is it possible that you could love both football and hot dogs at the same time? Sure, a person could love them both. Those are not mutually exclusive. In order to be mutually exclusive, the two events cannot happen at the same time. How about this? Is it possible to roll 2 dice and get a sum of 4 and a sum of 10 at the same time? No. Impossible, right? So we would say the probability, the chances of getting a 4 and a 10, it's impossible. Those are mutually exclusive events. Okay? If you have a situation where you have mutually exclusive events, and you're trying to figure out the probability that one event happens or another event happens, it's as simple as just adding up their individual probabilities. So I don't know, let's say I'm playing some dice game with somebody. Okay? And I'm going to win if I roll a 4, 5, or a 6. Otherwise, the other person's going to win. Okay? If I want to find out the probability that I roll a 4 or a 5 or a 6, since they're disjoint, since they're mutually exclusive, I can just use this formula. So the probability of getting a 4 or a 5 or a 6 is the probability of getting a 4 plus the probability of getting a 5 plus the probability of getting a 6. We put those probabilities in here. It's 3 over 36 plus 4 over 36 plus 5 over 36. That's a total of 12 over 36, or 1/3. So in the long run, there's a 1/3 chance. 1/3 of the time, when you roll 2 dice, you're going to get a 4, 5, or a 6 in the long run. Okay. Our first rule on how we calculate the probability of something, if we know all of the elements of the sample space, and we know how many times our event can happen, just make that fraction, you've got your in the long run probability. In our 4 rules, probability's got to be 0 to 1, inclusive, can be 0, can be 1, can't be outside of it. Probability of the entire sample space, when we draw our charts, this guy's always got to be equal to 0. Probability of something not happening is 1 minus probability above, and then this is the biggie here. If you have events that are mutually exclusive, and you're trying to find the probability that one event happens or another event happens, you can simply add up those individual events. Okay?